It's a great pleasure to welcome you all here this afternoon in the presence of the Clays. Very pleased to be part of this afternoon session. Our first speaker is Professor Ben Green, who needs almost no introduction. He's the Waynflete Professor of Pure Mathematics at Oxford, came here a year ago, and he came to prominence for his great results, much in combination with Terry Tao, on arithmetic primes and progressions. He's the recipient recently of the Sylvester Medal of the Royal Society, which I think is the only thing I can, of his medals that is not on Wikipedia yet, so say something new.
Thanks, Andrew. I hope I'm audible without a microphone. I'm going to give that a go. So what I want to talk about today is higher order Fourier analysis. Which is something that I've been interested in and working on for the last 10 years. And I want to say a little bit about what it is and what the current state of it is and how we would hope, what state we'd hope this will be in 10 or 20 years' time. So higher order Fourier analysis is, in one sentence, it's a tool for understanding systems of linear equations in sets of integers. And I suppose it's been motivated by two specific types of problem. So the first is understanding a particular system of linear equations in an arbitrary set of integers. So this is combinatorial problems connected with arithmetic progressions. And in particular, a very famous theorem called Semirades theorem. So Semirades theorem is the statement that if you take a set of integers of positive density in a suitably defined sense, so sets of integers with positive density contain arbitrarily long arithmetic progressions. So contain k-term arithmetic progressions, henceforth abbreviated APs, for all values of k. So that's been a major motivation for the development of the tools that I'm going to be discussing. And then somehow the other motivation has been questions about the primes. Questions about prime numbers. And there again, arithmetic progressions were something that have been quite prominent. So for example, this question about arithmetic progressions of prime numbers. But the theory's now become much more general than that. So interested in questions about fairly arbitrary linear systems of linear equations with prime solutions. So I'll be a bit more specific about that later, and I hope to have time to talk about a recent development which comes from this, about large gaps between prime numbers, consecutive prime numbers. So that's some of the motivation. So it's been understood for really a long time that traditional Fourier analysis is a tool that's well equipped to studying essentially a single linear equation in a set. So traditional Fourier analysis and this is called different things by different people. It's called the method of exponential sums, or the Hardy-Littlewood method. Exponential sums, Hardy-Littlewood. So this is good for studying one linear equation. In a set A. So for example, you could use this to study three-term arithmetic progressions. So a three-term AP. That's given by three equally spaced elements. That's the equation x plus z equals 2y. So x, y, and z are in arithmetic progression if they satisfy this relation. Or other equations, for example, or the Ternary-Goldbach conjecture, something that we've been hearing a lot about lately. Ternary-Goldbach problem, and that's to do with solving this affine linear equation in prime variables p1, p2, and p3. So what do I mean by traditional Fourier analysis is good for that, other than that you can look at a large body of papers which use these techniques to say something about those problems? Well, I can be a bit more specific about this, and that's what I want to do now. So let me take a set A. Let's take two sets, in fact. So take two sets, A and B. These are subsets of 1 up to n, which I will denote by n. And I want to compare how many three-term arithmetic progressions they have. So I'll give that a name. So T3A, which is the number of three-term progressions in A, with T3 of B. And it's a fact that I can do that in a useful way with the Fourier transform. So we'll define the Fourier transform first. So define the Fourier transform of A. So we generally write this as 1 sub A hat theta. It's just the sum between 1 and n. In fact, just over the set A, so I use this letter 1 sub A of n, just is the characteristic function of A, times e to the minus 2 pi I n theta. So e of t, e to the 2 pi I t. And of course, to find the Fourier transform of B similarly, then it's a fact that if the Fourier transforms of A and B are close, so I'll be a little bit rough about it first. I could be a bit more precise maybe in a moment. So if the Fourier transforms are close pointwise, and this is, sorry, for theta between 0 and 1, or modulo 1, R mod z. So if the Fourier transforms are close pointwise, then the counts of arithmetic progressions are close. Then T3 of A is roughly T3 of B. So let me just be a tiny bit more precise. This isn't too important, but if the difference, the sup over theta of the difference between these two things is at most epsilon times n, the trivial band for this would be 2n, I suppose. So this is supposed to say that they're close. Then the difference between the number of progressions they have is also small. So I forget exactly what, something like epsilon to the 1/2 times n squared. And again, the trivial bound would be basically n squared. So two sets whose Fourier transforms are close have a similar number of 3-term progressions, and this is very useful for counting how many progressions there are in various sets, be they sets of positive density or specific sets like the primes. I don't want to prove that, but somehow, well, the reason it's true is that there's a magic formula. So one reason this is true is a formula. So the formula is that T3 of A, number of 3-term progressions in A, is the integral from 1 to 0 of essentially the Fourier transform of A cubed. So this is a fun exercise, just using the orthogonality relations for the additive characters. So higher order Fourier analysis starts from the observation that this is not true for more complicated types of linear configuration. So in general, Fourier analysis fails for systems of 2 or more equations. And, well, a nice example of a system of 2 equations is a 4-term arithmetic progression. So, for example, 4-term arithmetic progressions which are just systems of quadruples x1, x2, x3, x4, satisfying this pair of equations, x1 plus x3 equals twice x2, and x2 plus x4 is twice x3. Now, obviously there is, well, pretty obviously, there is some kind of formula for the number of 4-term progressions using the Fourier transform, just because the map between sets and their Fourier transforms is 1-to-1. You have an inversion formula, so you could just write down some kind of formula. But it turns out that that formula is not useful, and I can be precise about the sense in which it's not useful, which is that the analog of what I suggested here fails. So here's a key example. Let T4 of A be the number of 4-term progressions in A. And I claim that there are sets A and B contained inside 1 up to n, whose Fourier transforms are close, pointwise, but the number of arithmetic progressions is quite different. And somehow the nature of this example is quite critical in motivating the rest of what I'm going to say. So let me show you what the example is. We take A to be, well, let's fix alpha equals 1/10, let's say. So we're going to take 2 sets of density 1/10. So A is a random subset of 1 up to n of size n over 10, which could mean something like you just pick elements independently with probability 1/10. And then B is a deterministic set, something like the set of all n between 1 and n, for which the fractional part, or the distance to the nearest integer of n squared times a suitable irrational number, it doesn't really matter which one, is less than or equal to 1/5. So here, this means distance to the nearest integer. So those two sets, if you plot them numerically, then it somehow actually looks quite difficult to distinguish between a typical instance of A and a set such as B. And the Fourier transform is not a good tool for doing that. So it turns out that this is not the easiest of exercises, but it's a fairly standard type of exercise. That the Fourier transforms are very close pointwise. And somehow that's not surprising. The set B is a sort of quadratically correlated set. So why should it somehow see these additive, these linear characters, e to the 2 pi I n theta? Well, that's a tricky exercise, but an entirely reasonable statement. And then it turns out that, however, B has many more 4-term progressions than A. And the reason for that is that there's the following observation. We have the following identity, n squared minus 3 times n plus d squared plus 3 times n plus 2d squared minus n plus 3d squared. Actually, let me make that 1 over 100, if you don't mind, just to make this a bit more convincing and even true. So that we have this identity equals 0, and it follows easily from that if n plus d, and n plus 2d all lie in B, then there's a constraint on where n plus 3d must lie. That implies that the fractional part of n plus 3d squared times root d is bounded by 7 over 50, by the triangle inequality, 7 being 1 plus 3 plus 3. So, in other words, if I've already got 3 elements of an arithmetic progression in B, n, n plus d, and n plus 2d, the fourth element is pretty keen to be in B as well. It definitely doesn't behave like a randomly distributed, independent element of 1 up to n. So n plus 3d is somewhat likely, somewhat more likely than random, to be in B. And all that can be made rigorous with quite a bit of effort. Okay, so to summarize so far, Fourier transforms, or correlations with additive linear characters, are a sufficient tool for understanding 3-term arithmetic progressions, but they're not a good enough tool to understand 4-term progressions, and as it turns out, pretty much any other system of more than one linear equation. So the basic question of higher order Fourier analysis, is to describe a collection of higher order characters which play the role, which do for 4-term A progressions and other linear systems, what the additive characters did for single linear equations. So to be a bit more precise about it, we might ask for a little more precisely. Give a set phi, and as it turns out, phi will have to depend on certain parameters, but so let's say phi of delta, such that, well, if I've got two sets A and B, and if when I test them against elements of phi, so the inner product, I'll write down what this is in a moment. So for all phi, then the number of, say, 4-term progressions in these sets differs by at most delta times the trivial bound. So here this inner product is probably just what you think it is. Inner product of F1, F2 is just the, well, it's the average of F1 times F2 bar. So that's somehow the basic question. And the solution in the case of single linear equations is, well, you can take phi to be just the additive characters. The example that I showed you here gives some kind of hint as to what sort of answer we could hope for in general. So maybe a naive guess might be that if I'm interested in studying systems of D-linear equations, so if I'm interested in a certain system of D-linear equations, then maybe I can take phi to be the polynomial phases of degree D. So I could take phi to be the collection of all e to the 2 pi I p of n, such that the degree of p is at most d. Why would I say that? Well, if you think about it for a little while, the two sets A and B that I showed you on this board here, the random set will not have any particular correlation with say, a quadratic phase function, whereas the second set I showed you, B, will have a very strong correlation with a particular quadratic phase function, e to the 2 pi I n squared root 2. So somehow this example would motivate this guess. But it turns out that that guess is actually incorrect. And that you necessarily must involve somewhat more complicated functions in, as higher order characters. So the higher order characters are more complicated than this. And it's historically quite interesting how this came to be realized. It sort of came from two different sources. Actually, well, I'll say something about the work of Tim Gowers in a moment, but he had examples of sets A and B for which when you test them against all quadratic characters, they look the same as well, but which still don't have roughly the same number of 4-term progressions. And then somehow in parallel with almost everything I'm saying, there was a lot of work in ergodic theory. And this predates a lot of Tim Gowers' work. So intuition coming from ergodic theory, and in particular the theory of what's called characteristic factors. led to a correct guess for what this set of higher order characters should be. So this was a big body of work in ergodic theory developed by people like Furstenberg and Weiss, and then more recently by Hofstra and Ziegler. And maybe I'll take just a couple of minutes to just explain one or two things about that. I don't want to go into too many details, but the basic setup is that you have some, as you often have in ergodic theory, you have a measure-preserving system. So it's some set X, which in these applications is a compact metric space, together with a transformation T and a T-invariant measure mu and some sigma algebra. So this is a standard type of object, measure-preserving system. And instead of things like arithmetic progressions, what one wants to understand is analogues of, so here's an analog of a 4-term progression. This would be something like the limit, as n tends to infinity, of the average, the ergodic average, of some integral over the space of a set. And now somehow the shift in the arithmetic progression is given by, instead by this map T from X to itself. And the main result of this work of Hofstra and Ziegler is that you can understand averages like this by projecting from this measure-preserving system onto a very particular kind of factor. So it can be understood via projections of this set A, which here is going to be some measurable set, so 1A, onto very special, very structured subfactors, factors of x mu t b, by which you mean basically a sub-sigma algebra of B. Another way to think of this is that you just have some map to a different space, which will be a much more structured space. And you're projecting onto the space of functions which are pullbacks of functions on this much more structured space.
Your writing is getting very, very small.
Is it? I'm sorry. Yeah, I was very scared of using this board here because I know that you can't see it from here, but maybe I'll just do that anyway. It means... Yeah, so I mean, all I want to say from that board is that there's an analog in ergodic theory of arithmetic progressions, and you can count them by projecting onto a certain type of factor which was understood in ergodic theory by Hofstra and Ziegler. So these factors have a particular structure. These factors have a particular structure. They are inverse limits of what are called nil sequences. Well, nil systems. So I shall tell you what a nil system is because it is also relevant to what these higher order characters are. So a nil system is a particular type of dynamical system, measure-preserving system, in which the space X is the quotient of a nilpotent Lie group by a lattice. So where G is a nilpotent Lie group, so e.g. the Heisenberg, And then gamma is a lattice in there. And the map from the space to itself is given by right multiplication by an element of the group G. So by some fixed G. So at the moment I've been presenting this as though it's some kind of analogy, which in a sense it is. I mean, this ergodic setting, I've just said that these look a bit like arithmetic progressions. There is actually a more formal connection between arithmetic progressions and things in subsets of sets of integers and these measure-preserving systems, but it's not a completely tight correspondence. So think of it as just an analogy. But this result of Hoston, Krah, and Ziegler very much motivated the answer to this question of what should we take as our higher order characters. So this very strongly suggests an appropriate definition of higher order characters. So let me show you what that definition is. So it's something called a nil sequence. An S-step nil sequence is a function phi from the integers to the complexes of the form phi of n is f of g to the n, where f is basically a function it's a function on a Lie group G nilpotent of class S, Lie group G, which is automorphic with respect to some lattice. Gamma in G, which means, well, just periodic really. So f of gamma times G is just f of G. And well, this G here is some fixed element of the group G. So that's a definition that's motivated by this work that was done in ergodic theory, understanding characteristic factors of things that look like ergodic analogues of arithmetic progressions.
Sorry, and this definition of the little g is always the same in the periodicity and also in
Yeah, no, that's extremely bad mathematical notation. Maybe I should write A here. The automorphic condition is for all, this is for all G in G, and gamma in the lattice gamma. And then when I come to define the sequence, I fix in advance an element of the group. Now, one thing I want to remark about this is that in hindsight, it's sort of a bit natural in the sense that I can classical Fourier analysis is a special case of this. So when s equals 1, and you can take, so G is just R, it's an abelian Lie group, which is nilpotent of class 1, if you like. And gamma is the integers, and then f from R to C is just the usual additive exponential. Then you recover the usual the additive characters. So in a sense, at least in hindsight, this is a natural notion of higher order character. One thing that's not so apparently natural, and I don't really know, this is one sort of open problem in the theory, is that these functions f, which we had for additive characters, are very specific. I mean, e to the 2 pi it is a very specific kind of function. Whereas in this definition of nil sequence, I've just allowed an arbitrary function. I mean, usually you'll take it to be nice, sort of smooth or something, but it is a fairly arbitrary function. So it's quite a bit more general than these specific additive characters. So as I said, this specializes to the case of usual Fourier analysis. What's less obvious, perhaps, or definitely less obvious, is that it also includes the naive guess for what higher order characters should be. These quadratic exponentials and exponentials of polynomials are also special cases of this. So a harder exercise is that quadratic or polynomial phases such as e to the 2 pi I n squared root 2 can also be realized this way. But to realize, for example, that phase, e to the 2 pi I n squared root 2, you can't do it with G being abelian. You'd have to pass to a two-step, a class 2 nilpotent group like the Heisenberg group to construct this function that way. So the claim is that these somehow are the nil sequences of class S somehow are the appropriate higher order characters for systems of S linear equations. Now, it's in this claim, both the statement and the proof of it, that I regard this subject of higher order Fourier analysis as very much unfinished. So although this is a true statement, many details of how the details of how it works are very unsatisfactory. So let's first of all say, what does this mean? So to return to this question here, if I have two sets A and B, and if when I test them against all class 2 nil characters, so if this is at most delta primed for all phi which are two-step nil sequences, sorry. Then indeed the number of 4-term progressions in A and B is the same, or up to delta. So T4 of A minus T4 of B is at most delta times n squared. So that's what I said. These class 2 null sequences are a sufficient set of characters to determine 4-term progressions. But unfortunately, this statement cannot be true without, well, it's useless without some further quantification. In fact, it's not true without some further quantification. So in fact, there are no interesting sets A and B which, when tested against all nil sequences phi, their inner products agree. Because in fact, the way I've set it up, literally every function from 1 up to n to the complex numbers is one of these two-step nil sequences. And that comes from this unspecified function f. So you need to insert an additional notion of complexity. And I'm not going to go into what that means. So of complexity at most some function, let's call it w of delta. I mean, otherwise the statement's true, but it has no content. Whereas if I only want two sets that look the same when tested against nil sequences of bounded complexity, then I have a chance at least of a non-trivial statement. So the proof of this is very long and complicated. And it leads to just atrocious dependencies of the various parameters that I've mentioned there. So it leads to terrible dependencies on delta primed and w of delta on delta. So it's somehow resolving these issues, all of them, namely finding a proof that's natural. I think the statement of this thing is quite natural. The statement that there should be this quite easily described set of higher order characters is quite natural. The proof that we currently have of this is not natural. And maybe if you find the right proof, then you'll also find decent dependencies here. So I won't say anything about the proof other than that it's inspired by work of Gowers. So Tim Gowers' work on Semirades' theorem. So one way of describing what Gowers did in his work is he described at least some non-trivial class of functions phi that can take the role of these higher order characters. They're nowhere near as thin and structured a class as the ones I've described, these nil sequences, but they're enough for his purposes. So actually they're just functions that are basically piecewise constant. So Gowers showed that if two sets, when you test them, test their inner products against functions that are piecewise constant on somewhat long intervals, then they have a comparable count of 4-term arithmetic progressions. So in the last 10 minutes, I want to say something about where this has led us to. So applications to primes. So what Terry Tao and I have been developing over the last 10 years is the theory of these higher order characters and how they relate to prime numbers. And the main application of that is a big theorem, which is joint work of Tao and I, together with another joint paper with Ziegler. And what this gives is an asymptotic count of pretty much for any system of linear equations in the primes. So given any non-degenerate, whatever that means, system of linear equations, we can basically count how many prime solutions there are. We can give an asymptotic for the number of solutions in primes. Now, what does non-degenerate mean? It basically means that we've failed to solve the really famous open problems like the twin prime conjecture. So somehow the equation x1 minus x2 equals 2 is degenerate. But a lot of other systems are not degenerate. So we can give an asymptotic for the number of solutions of primes in reasonable domains, in a reasonable domain. And I want to mention, well, how does the proof of that go? It's very complicated. But the basic idea is that once you've set up this machinery of higher order Fourier analysis, you're then reduced to the task of understanding how the prime numbers, or the characteristic function of the prime numbers, interact with these higher order characters, these nil sequences. And we invented some machinery that will allow you to do all that you need in that regard. So here's an example, and it seems like a somewhat silly example. The number of (100-term) progressions of primes. So let's call them x plus d up to x plus 99d, in which all of the 100 terms are prime. And, well, I kind of want to say, and the common difference is prime, but that can't happen. The common difference can't be prime because then, well, for example, the first two elements of the sequence, unless the common difference was 2, would be 1 odd and 1 even, so that's never going to happen. But you can do almost as good. So d is 100 factorial times a prime. So I call that basically prime. Sort of basically prime is something. And all these things are less than or equal to x. So it's asymptotically x squared over a certain function that's natural if you know the prime number theorem. So log x to a certain power, so the minus 101 times a constant, for some constant that you can give explicitly. Don't worry too much about that, but the main point I want to take from this is that we can upgrade our theorem from 10 years ago, saying that there are infinitely many 100-term progressions of primes, to insist that the common difference of those progressions is almost prime as well, basically prime. Now, why would you want to do that? Well, an answer to that question is that it allows you to improve the bounds on long gaps between primes. So I shall have to be rather brief here. There's a long story and history to tell here, but I'm going to get fairly quickly to the punchline. Let g of x be the largest gap between primes less than or equal to x. So what can we say about g of x? Well, a trivial result, if you regard the prime number theorem as trivial, is that g of x is at least basically log times x. There are x over log x primes less than x, so some two of them must have a gap at least log x. And the conjecture is that g of x is less than or equal to log squared x times a constant. But progress on this has really hovered around trying to improve the trivial lower bound to something that's a bit less trivial. And it was stuck for a long time. In 1938, result of Rankine is that g of x is bigger than log x times a certain function which does at least have the decency to tend to infinity with x, albeit not very rapidly. So log x times a quadruple log over log x squared. And so it's a bit better than log x. But this bound proved to be extremely stubborn to improve this bound, and in fact it was not improved by more than a constant factor here until very recently. And then suddenly, within a day of one another, there were two independent proofs of a bound that's better than this by something that at least tends to infinity. So a function tending to infinity times the above. So these proofs were due to, well, one team was Kevin Ford, myself, Connie Argin, and Tao. And it was also done simultaneously by James Maynard, now here at Oxford. And actually, Maynard's argument's better, I freely admit that. However, the two are quite different, and I wanted to show you just one or two ideas, one idea from our argument, because it uses all of this machinery of higher order Fourier analysis. So how do you find large gaps between consecutive prime numbers? Well, you find long strings of composite numbers, of course, and that's done via something called the Jacob-Stahl problem. And the aim in this Jacob-Stahl problem is you want to start with the interval 1 up to y, and you want to remove all of the elements of that interval by sieving modulo primes p. Or in other words, cover by congruences AP mod p where these primes p are less than or equal to some x, and there's at most one of those congruences for each p. So p is prime. Well, you can do this with y equals x, of course. Just take AP to be 0 for all the primes less than x. But the aim of this Jacob-Stahl problem is to beat that and do it for larger values of y. For y as big as possible, you want to cover that interval by congruences modulo different primes p. What's that got to do with constructing long strings of composite numbers? Well, if you can do that, so then you take the numbers m plus 1 up to m plus y, where m is congruent to minus AP mod p for all p, which you can do by the Chinese remainder theorem, and those will all be composite numbers. So there's at least a one-way relation. It's not a two-way relation at all, but this is one method for constructing long strings of composite numbers. And really, it's the only method that we have at the present time. So I like to think of this as, instead of covering, I like to think of it as sieving. So what I want to do is, I'm presented with the primes p less than or equal to x, and for each of them I get a congruence class mod p, and I'm allowed to sieve out by that congruence class, and I want to destroy everything. And here's a recipe for doing that. So start with 1 up to y. So it comes in 4 steps. So first of all, I will sieve by the congruence class AP equals 0 mod p for p in a certain range. So p between log x, it turns out, and a certain parameter z. That z's just a parameter, I won't tell you what it is. Some parameter, which must be selected. So what happens when you do that? Well, you still have the primes. So if you're a prime less than or equal to y, unless you're also less than z, which is not going to be many of the primes, then you still remain when you've done this sieving. And then some other numbers called the z-smooth numbers. So the z-smooths are numbers all of whose prime factors are greater than z. And there are not many of these if you choose things properly. So let's just suppose that I've done this little preliminary sieve and I'm left with just the primes. Well, then there's a second step, which I don't really need to tell you about. It's a kind of random sieving. And then I'm left with slightly fewer primes. But then the gain comes in the third step, where you notice that if you have one of these, if you have an arithmetic progression of, say, 100 primes between 1 and y, whose common difference is also a prime, well, as I said, that can't happen, but it could be basically prime, then I can use that arithmetic progression to sieve out 100 elements at a time. So using basically prime progressions, we can sieve out 100 of these primes at a time. So if you have an arithmetic progression of length 100 whose common difference is 100 factorial times p, use an appropriate congruence mod p to destroy all those 100 elements. And this is where the improvement over previous bounds comes. Previously, you could only do 2 in place of 100 or 1,000 or what have you. So to finish, let me preempt a question that sometimes gets asked, which is, what is the function that tends to infinity? By giving you the negative news that it's, I believe, the worst function ever to have appeared in number theory. And so it's actually a completely ineffective function. It cannot be specified at all. And there are two distinct sources of the ineffectivity. One is something called a Siegel zero, which is something that's related to the location of zeros of L functions in analytic number theory. And the second is to do with the sorry state of this theory of higher order Fourier analysis that I described. Because somewhere up there, I had, right at the top, I said that there were terrible dependencies of these various parameters that we currently have for this higher order Fourier analysis. And actually, I meant that they really are terrible. They're actually ineffective if you're dealing with nilpotent groups of class bigger than 2. So class 3 and higher. So that's ineffective as well. And if you put two ineffective things together, it just, well, it's even more ineffective than it was before. OK, so I'll stop there.